Today, wow, we're diving headfirst into maybe one of the biggest tensions in modern physics. You've got general relativity on one side. It paints this picture of a local universe, nothing travels faster than light, period. But then quantum mechanics comes along and throws this curveball, this spooky action at a distance.
Yeah, spooky action. It seems like a flat-out contradiction, doesn't it?
It really does. And that sets up the big question for us today. Does the chance of two particles staying entangled actually depend on how far apart they are in spacetime?
And, well, as you can probably guess, it's not quite a simple yes or no. It's more like peeling an onion. There are layers to this.
Hmm.
Our mission really is to explore how this entanglement-distance relationship changes. We'll start with the pure theory, then look at what happens in real experiments, and finally, push into the really wild stuff, the frontiers of quantum gravity.
Okay, sounds like a journey. So, to keep us on track, here's the plan. We'll kick off with the basics, what entanglement and spacetime are, then the ideal world, the theory. After that, the messy reality of experiments. We'll also think about spacetime maybe not being just a background, but an active player. And finally, yeah, get into that revolutionary quantum gravity idea that could change everything. Sound good?
Let's do it.
All right, first principles, quantum entanglement. Let's unpack that a bit for everyone. Imagine you've got two particles, maybe more, and they interact in just the right way. They become linked. They form this single unified system. It's holistic.
Right. And the key is you can't describe them individually anymore. They're not separable. Instead, they're in what we call a superposition of possibilities, like that famous Bell state.
Yeah, heroes A plus 11O.
Don't worry too much about the symbols, but what does that mean?
It means they're in a state where either both particles are, say, spin up or both are spin down at the same time until you measure them.
And the crazy part is the correlation,
Right.
no matter how far apart they are. Exactly. You measure one, find it spin up, and instantly you know the other one is spin up too, miles away. Instantly.
Or spin down, same deal. Which, yeah, sounds instantaneous.
It does, and that's what bugged Einstein so much, his skooky action at a distance.
Right, the EPR paradox back in 35, he felt this violated local realism.
Yeah, the idea that things have definite properties locally and influences can't travel faster than light, Einstein thought quantum mechanics was, well, missing something. Incomplete.
Okay, so that's the quantum weirdness. Now contrast that with the other pillar, general relativity.
Right. Einstein's other masterpiece. Here, space-time isn't just there. It's not a passive stage. It's this dynamic four-dimensional fabric. You know the saying from Wheeler, matter tells space-time how to curve.
And curved space-time tells matter how to move. Yeah. Gravity isn't some mysterious force pulling things.
It's just the shape of space-time itself.
Yeah.
And crucially, this space-time has rules, strict rules. It's defined by the light cone. Basically, things in your past can affect you, and you can affect things in your future.
But only within the boundaries set by the speed of light.
Exactly. Nothing gets outside that cone. No information, no influence travels faster than c. That's locality, baked right into the geometry.
Okay, so here's the clash. Entanglement seems instantaneous. Relativity says nothing is instantaneous. How does the universe handle this?
Does entanglement break the cosmic speed limit? That's the million-dollar question, isn't it?
Or is there some kind of loophole or a misunderstanding?
Well, there's a crucial piece of the puzzle called the no communication theorem. Think of it as a kind of peace treaty.
A peace treaty between quantum mechanics and relativity.
Yeah. It's a formal proof, actually. It shows that entanglement, despite appearances, cannot be used to send any controllable information faster than light.
How does that work if the particles are instantly correlated?
It boils down to randomness. Quantum measurements are probabilistic. Let's say Alice measures her particle. She gets up or down, totally random 50-50 chance. She can't force a specific outcome to send a message, like Morse code.
Okay, she just gets whatever she gets.
Right. And Bob, miles away, measures his particle. He also gets random results, up, down, up, down.
Yeah.
They only see the perfect correlation, that they always got the same result when they compare notes later.
Ah, so they need to communicate normally, like over the phone or internet.
Which is limited by the speed of light. So the correlation is real, it's non-local, but you can't exploit it for faster-than-light communication.
Got it. So the universe can have this spooky non-locality.
But causality, the rule that cause must precede effect and nothing travels faster than light, is still safe. That distinction is absolutely key.
Okay, that treaty holds. So let's move to the ideal view. In pure quantum theory, does distance matter at all for entanglement itself?
Theoretically, no. Not really.
Yeah.
Within that sort of pristine mathematical framework of quantum mechanics, Hilbert spaces, state vectors, all that, there's just no term in the equations for spatial distance weakening the entanglement.
Seriously. It's just
Yeah.
not a fact.
Not fundamentally. The strength of the correlation, like in those Bell tests, depends on how you set up your detectors, the measurement angles, not how many miles are between them. In a perfectly isolated system, which, okay, doesn't really exist, but in theory, entanglement is like a topological property. It just is, regardless of separation.
Wow. But that sounds almost too clean for the real world. How well has this actually been tested? Because that's a pretty wild claim.
Oh, it's been tested incredibly rigorously. It's one of those solid predictions we have. It goes back to John Stuart Bell in the 60s. He came up with this famous inequality.
Right, the Bell tests, a
Yeah.
way to actually measure if local realism or quantum mechanics matches reality?
Exactly. And quantum mechanics predicts you should violate Bell's inequality. Local realism predicts you shouldn't.
And the results.
Overwhelmingly violated. Quantum mechanics wins. Every time, essentially.
And this led to the 2022 Nobel Prize, didn't it? For Clauser, Aspect, and Zeilinger.
That's right. Giants in the field. Clauser did one of the first really convincing tests back in '72. Showed the violation clearly over maybe 5 meters or so.
Okay, 5 meters. Still lab scale.
Yeah, but then Elaine Aspect in '82 did something incredibly clever. He worried about loopholes. What if the detectors were somehow communicating faster than light or had preset instructions?
The locality loophole.
Exactly. So he set up to change the measurement settings, the
Yeah.
polarizer angles, while the photons were already in flight. Super fast switches.
Whoa! So there was no time for any hidden signal to coordinate the outcomes.
Precisely. Over about 12 meters that time. It really slammed the door on that particular loophole.
And Zeilinger took it even further.
Oh yeah. Zeilinger's group tackled the freedom of choice loophole. What if the choice of measurement settings wasn't truly random, but somehow correlated with the particle's creation?
That sounds paranoid.
Well, you have to rule everything out. So in their cosmic Bell test, they used light from incredibly distant quasars,
Billions of light years away.
billions, to randomly determine the measurement settings, the idea being there's no way anything on Earth could have influenced both the quasar and the entangled particles locally.
That's incredible. And we've even tested it with satellites now, right? Like Mischius.
Yep, over 1,200 kilometers. The results hold up. Distance, in principle, doesn't kill entanglement.
It's fascinating that pushing the distance further wasn't just for breaking records. It was fundamental to proving the lack of a distance effect.
Exactly. It helped rule out hidden variables or faster-than-light coordination.
Okay, so theory says distance doesn't matter. Experiments confirm it, even over vast distances. But there's always a but, isn't there? What about the real world, the practical side?
Ah, yes. The messy reality. Decoherence.
Let's unpack that, because in practice, entanglement seems incredibly fragile.
It is, because no quantum system is ever truly perfectly isolated from its environment. Ever.
Right. There's always
Yeah.
stuff around.
Always stuff. Stray photons, air molecules bumping into things, thermal vibrations, you name it. And these interactions essentially measure the quantum system without us intending to.
And that disrupts the delicate quantum state, like the superposition or the entanglement.
Precisely. It's not that the entanglement link itself breaks cleanly. It's more like the information about the correlation. It leaks out. It gets scrambled and lost into the wider environment. The system stops behaving quantumly and starts looking classical.
Like trying to whisper a secret across that noisy room again. The message gets drowned out.
A good analogy. And here's the subtle link back to distance.
Okay.
While entanglement itself isn't inherently distance dependent, the longer a particle travels or the longer it exists.
The more chances it has to bump into something from the environment.
Exactly. More distance means more time, which means more opportunity for interactions that cause decoherence. So distance becomes a sort of proxy, a practical factor that increases the probability of entanglement being lost.
Ah, okay. So the answer to our original question is no, not in principle.
But yes, very much so in practice. Because the further you try to send an entangled particle, the harder it is to protect it from decoherence.
And that's the massive headache for building things like a quantum internet, right?
Absolutely. It's probably the single biggest engineering hurdle. You get photon loss in fibers, signal degradation. It drops off exponentially with distance.
So how do scientists even try to deal with this? You can't just amplify a quantum signal like a classical one.
No, measuring it to amplify it would destroy the quantum state. That's where things like quantum repeaters come in.
Okay, what are those?
The basic idea is you don't try to send one fragile photon the whole distance. You break the distance into shorter segments. You create entanglement between nodes across each short segment where it's more likely to survive.
Right.
Then, you use a clever trick called entanglement swapping at the nodes to link these shorter entangled pairs together. It's like building a chain.
Extending the entanglement without sending one particle the whole way. But that sounds complicated.
Oh, it is. It requires things like reliable quantum memories to hold the entanglement at the nodes while you set up the next link, plus just the basic stuff: extreme isolation, ultra-high vacuum, cryogenic temperatures, shielding. Scientists go to incredible lengths.
It really highlights how delicate this stuff is.
It really does.
Okay, so we have decoherence from the general environment. But you mentioned earlier that spacetime itself might be an active player, even beyond just providing distance for decoherence to happen over.
Yes, this is where we start bridging towards quantum gravity ideas. There are theoretical models suggesting that gravity itself might be a fundamental source of decoherence.
How would that work? Gravity causing decoherence?
Well, the idea is that gravitational interactions, even subtle ones between massive particles, could potentially carry away information about the particle's states, like which path information in an interference experiment. If gravity reveals which path the particle took, it can destroy the superposition needed for entanglement. And the strength of this effect might depend on the masses involved and their separation.
So the environment causing decoherence could actually include the gravitational field itself, even in a perfect vacuum.
That's the theoretical prediction in some models. It implies an intrinsic link between entanglement stability and the very structure of spacetime, the mass energy that defines its curvature.
And what about other gravitational effects like time dilation? We know clocks tick slower in stronger gravity.
Right, general relativity's time dilation. So imagine you have two entangled particles, but one is near a massive object and the other is far away.
Like one on Earth, one on a satellite.
Exactly. Their internal quantum clocks, the rate at which their quantum states evolve or accumulate phase, would tick at slightly different rates.
And that difference could mess with the entanglement.
It could potentially alter the specific character of the entanglement or reduce its fidelity over time. The effect is expected to be tiny for Earth's gravity, but
Near something like a black hole, it could be significant.
potentially yes. These are theoretical calculations, very hard to test right now. But they point towards gravity not just being a passive background, but actively influencing quantum phenomena.
It really feels like we're probing the boundary where quantum mechanics and general relativity meet, or maybe clash.
Precisely. Finding experimental evidence for gravity-induced decoherence or entanglement modification would be huge. It could be a window into the quantum nature of gravity itself.
Okay, that brings us to the really mind-bending frontier, quantum gravity. And this idea, ER equals EPR.
Yes, ER equals EPR. This is definitely out there, speculative, but incredibly thought-provoking. Proposed by Maldacena and Susskind in 2013.
So ER, that's Einstein-Rosen bridges, wormholes.
Theoretical wormholes, yes. Shortcuts through spacetime allowed by general relativity.
In principle.
And EPR, the Einstein-Podolsky-Rosen paradox, or spooky entangled particles.
So the conjecture is, what? That these two things are the same?
Essentially, yes. It proposes a radical equivalence. A pair of entangled particles, EPR, is geometrically connected by a microscopic wormhole, ER bridge.
Wait, so the spooky action is actually a physical tunnel through space-time?
A non-traversable one. That's absolutely crucial.
Non-traversable, meaning?
Meaning you can't send information or yourself through it. It connects the particles geometrically, perhaps through higher dimensions, but it doesn't allow faster-than-light signaling.
Ah, so it respects the no communication theorem. It doesn't break causality.
Exactly. It provides a potential geometric explanation for the correlation without violating relativity. It came partly out of trying to solve puzzles related to black holes, like the firewall paradox.
Okay, if this is true, it completely flips our thinking about distance, doesn't it?
It totally inverts it. If entanglement is this geometric connection, then maybe spacetime itself isn't the fundamental thing.
You mean space-time could emerge from entanglement?
That's the implication. Perhaps the fabric of spacetime is literally stitched together by a vast, complex network of quantum entanglement between fundamental constituents.
So the distance between 2 points isn't fundamental. It's just a reflection of how much entanglement connects them.
Or perhaps how little. High entanglement might mean close in some fundamental sense, even if they look far apart in our usual spacetime. Low entanglement might mean far. The question changes from how does distance affect entanglement to how does entanglement build spacetime and define distance?
Wow. Okay, that's a lot to take in. It makes distance seem almost like an illusion, or at least not the basic building block we thought it was.
It's a profound shift. Now, we have to stress, APR is a conjecture. It's explored in theoretical frameworks like AD-SCFT.
That's that mathematical duality connecting gravity theories with quantum field theories, right?
Right, a powerful theoretical tool. But direct experimental proof, we're nowhere near that yet. Maybe futuristic tests looking for tiny gravitational effects from entanglement. But that's way off.
Still, the potential is huge. A possible route to finally unifying general relativity and quantum mechanics.
That's the dream. That they aren't two separate theories, but maybe two different languages describing a deeper reality woven from quantum entanglement.
Okay, let's try and bring this all together. We started with a seemingly simple question. Does entanglement depend on distance?
And the answer is, well, layered. Layer 1. In the ideal world of pure quantum mechanics, no. Entanglement is theoretically distance-independent. Bell tests confirm this.
Okay. Layer 2?
Layer 2. In the real, messy, experimental world, yes, practically speaking. Distance increases the chance of decoherence, degrading entanglement. It's an engineering problem.
I had it, layer 3.
Layer 3. Considering relativity and gravity, spacetime isn't just passive. Gravity itself might influence or degrade entanglement. Yes, potentially fundamental.
And the final, most speculative layer.
Layer 4. At the quantum gravity frontier, maybe distance isn't fundamental at all. Maybe spacetime emerges from entanglement. So the question itself might be framed backwards.
From no to yes practically to yes maybe fundamentally to maybe the question is wrong, that's quite a journey.
It covers a huge range of physics, from foundational principles to the absolute cutting edge.
So thinking about this for you, our listeners, this deep dive has taken us right to the edge of what we know and even what we speculate. If distance, the very separation between things, might just be a macroscopic effect of entanglement, what does that really mean? Could understanding entanglement not just unlock quantum computing, but actually reveal the fundamental blueprint of reality itself? Something to ponder. Thanks for joining us on The Deep Dive.